Hi, today I'm going to present on a topic, a supervised learning solution for autonomous row following task in horticulture. So we are presenting from Norway, from a university called Norwegian University of Life Sciences. The motivation for our work is in horticulture, there are different ways of vegetation practices. And one common way is row-like structures like this, where the poles are used to make a systematic way to do harvesting. And then for other fruits like kiwi, there is another environment called pergola, which where they use ground poles to support the structures. And then we have orchards environment for fruits like apple and oranges, where trees are used for, and some supporting poles also used to make a symmetric alignment for harvesting task. Our motivation here is in all these environments, there is pretty much a standard RTK GNSS solution suffers due to the blockage of signals. And then the another assumption that all the fields are flat is not exactly true. So then we have issues with the 2D laser scanner based solution as well. And in orchards, we found that there are missing trees in the row. So in order to cope up with it, we try to propose a CNN based solution only using a camera sensor. So in row-like structure, the goal is for the robot to follow exactly in the center. So we call it center line following. And for the orchards, we call it sideline following, where the robot has to stay at a certain distance from either one side of the trees to do any kind of application. So in orchards, the test cases is we have trees with supporting poles, which are 2 meters in width, and we have another case which is like bushes with supporting poles, which are a little bit more wider than the last one. And then we have this missing tree cases, which we also added in our data set. So that the CNN can able to understand this variance in the fields and try to have a more generalized solutions. So we pretty much used uh, a standard CNN methods where we collected 500 images combining in different both indoor and outdoor cases. And this is how we annotated the case, and we call this as a drivable area. And drivable area is actually means that the robot can able to move forward to in that region without any collision. So this is a more generalized uh, approach, because other plants and everything changes over the period of time during the season. So we try to take a most common thing which doesn't change, and we try to make the CNN understand this. So this is the typical standard encoded decoded architecture, where we give an input RGB image, and we have a prediction with the drivable area region exactly specific predicted with their class number. This one is from ERF-net, which they use factorized convolution methods. We try to compare it with other CNN methods as well. And to collect the data set and also to test it on the field, we will use the same robot called Thorwald, and we have a sensor called Intel RealSense sensor with the RGB D camera. We also have a prism for the robot to track the trajectory, so that we can compare it with the ground route for in the motion planning side. And in the polytunnel, we have this kind of UV light treatment. So we have to make sure that the robot stays exactly in between the two poles to do the application equally on both the sides. And we have a GPU computer on board to collect the data and also to process and run it online as well. So these are some of the results in the orchards environment, where we can see actually it has different illumination conditions, different situations where we are rotating, keeping the robot at one side diagonally as well. And here there are no trees actually in one side, but still the CNN able to understand and try to predict the drivable region, not predicting the area from the neighbor rows. It is safe to go, but we, in order to stay to one lane to do one particular application, we try to train the data in such way, and the CNN can able to understand these differences and try to able to find it even in terms of shadows and stuff. And the main contribution here is we try to merge it with the indoor environment as well. So indoor is completely different situation actually, but what we thought is the drivable area is something it's not going to change. So we try to combine both indoor and outdoor together and find this region. So it's the same, it can able to find irrespective of the plants, uh, whatever the season that it whatever the growth rate, the drivable area is a constant thing. So the robot can use this information for moving further. So these are some results we compare with different CNN methods. We use ResNet with different layers, DarkNet, ERF, and MobileNet. The accuracy, everything is close to 90% for that particular class. So we consider that is good enough for the robot to trust these predictions. And the inference time is the actual time that it takes to predict the image. And we found that the ERF net is the fastest one with almost like 20 hertz, and dark net with 53 layers is 5 hertz. So even the 5 hertz one is more than enough, considering the robot speed goes at a very minimal speed doing particular operations. So this whole CNN method is actually feasible for real-time application. So there are some learnings. We try to make a more generalized solution combining indoor and outdoor, and it can able to perceive these differences. But our approach had some limitations. Some of them is called it works only when they are in between the rows. So it's good for in row movement, but when it reaches the end of the row, we have a headland where the robot actually has to make a U-turn to move to the another next row, neighbor row. So this headline area, we try to add it in the same similar fashion, but it actually worsen the performance because the features there are different and the action for the robot is different. So we try to take the headline moment as a different problem. This will be in the future, but we will keep on focusing on that. Another thing is ground truth estimation as well. The correct way to do is using a terrain surveying professional group to estimate the exact center lane, so that between the trees or between the poles, so that we can compare it with our predictions and see how well we predicted. But for now, we compared it with the human expert who is doing manual annotations, and we showed the accuracy values already. And then we also will try to find more environments to justify our robustness for generalization uh, climb. So besides that, the next moving forward, we try to estimate a guided center line. This is the future work. So once we have the center line with the directional value, so we can actually steer the robot using this information. So we propose the solutions, machine learning methods to only with the RGB camera, low cost, so to steer the robot inside the row in both indoor and outdoor. The next thing will be is to make an automated closed loop guidance, and we use the robot to go through the entire field. So this is the future work, and of course with the machine learning we need a good GPU system, hardware capability, and have to collect more data sets to be able to understand the perceived variance of the environment. So these are some of the factors which we have to always look into it. But the idea is to make a complete autonomous system for the robot only by machine learning. So this is the future work we are focusing on right now. So until then, thank you for your attention.